So 3.4 is related rates. Math 65. So I'm going to introduce you to an idea here. Let's say this is our good old, we're graphing y equals 3x. It's kind of steep. Let's say that's y equals 3x. I didn't like make hashtags or anything like that because that part's not the important part. Let's say you're a little bug crawling on this motherfucker. You're a little ladybug. You got little spots on your back and you're crawling along. And so your position at time t of the ladybug the x will have a position related to t and the y will have a position related to t. So I'm going to say like when x equals 0, just for an example, we're going to have t is -4/3. Seems like a weird thing to work with, but we're going to work with it. So if I solve this for 0, I could multiply, I could get 3t equals -4, and I get 3t plus 4 equals 0. And the reason why I got them equal to 0 is so that I could make the connection here that x, and these things have the same value, x equals 3t plus 4. So that's my function or position of x as it relates to time. Y of t is really going to be y of 3x. So when I do y of t, it's 3 times x of t. So y of t is going to give me 9t plus 12 when I multiply it by 3. I'm not testing you on this part, but it is, you will see it in Calc 2 and 3. This is called parameterizing the function with time. Whether t is in seconds or minutes or how long, it doesn't really say. We can, if we have a path of something going along a path, and it's actually moving, so it's at different positions at different times. This is like a real world application of graphing. We could parameterize it in terms of time. Well, I've got x of t and y of t up there. What if I do d dt of x of t? I have the time derivative of 3t plus 4. And we'll do the time derivative of y of t. This is just 3. And this is 9. If I look at them in terms of this equation, y of t equals 3 times x of t, and I do the time derivative here, I get dy dt equals 3 dx dt. And we can see that's true from right here. 9 equals 3 times 3, and that 3 is dx dt. So I can see it from there. The rate of y is related to the rate of x. That's what this section's on, related rates. So this is like the position of the ladybug with respect to y is changing 3 times faster than the position of the ladybug with respect to x. I'm not going to do anything else with this t. You're going to see parameterizations later. We're just going to look at related rates in general. But I thought maybe showing you how parameterizations of stuff work now will help you in the future because it does apply here to related rates. So if you wanted a summary, in summary, if two variables are related, by a formula or function or something like that, then their rates of change are related. And the way we're going to use this, we can use known info about one rate of change to determine the value of the other. This is the prior section is word problems. Because it's like, how do you use this? So, example. We have a spherical soap bubble. That is expanding. How fast is its radius increasing? if air is being blown into the balloon or bubble, at a constant rate of 3 cubic inches per second. Let's look at specifically at 3 seconds, or specifically when the radius is 3 inches and 6 inches. So, what is changing here when I say the air is being blown in at a constant rate of 3 cubic inches per second and the bubble's getting bigger? What would we say is changing, like in terms of the bubble? If a circle is getting bigger, just like a two-dimensional circle is getting bigger, what's getting bigger as it gets bigger? Area. Now let's turn that into a sphere. Volume. The volume is changing here. This constant rate of 3 cubic inches per second is a change in volume. And we're asking about how it relates to the radius increasing. We need a formula that connects volume and radius for a sphere. Does anyone know that offhand? Okay, I do. This is one of those that comes up often enough in your entire calc sequence that you'll eventually have this memorized. The volume of a sphere is 4/3 pi r cubed. I'll call that V for volume. So we have something equals 3 inches cubed per 1 second. The top thing is a change in volume. So we're going to use D. The bottom is a change in time, so dt. How fast is its radius increasing? That's what we're being asked right here. What am I looking for in terms of this equation?
time? Or no?
It's related to time. It's the change of radius with respect to time. So we're looking for, if we use R for radius, we're looking for dr dt. So we start with V equals 4/3 pi r cubed. And we're going to take the time derivative of both sides. This is like doing an implicit differentiation. I take the derivative of this, the derivative of that is just 1, and then the derivative of V is dv dt. The right side, I have 4/3 pi, and then I take the derivative of r cubed. The 3 comes down, the exponent drops to 2, and then I got to do dr dt. So it's like doing implicit differentiation on both sides. If I were to clean this up, I have dv dt equals, it looks like the 3's cancel, and I'm left with 4 pi r squared dr dt. I just had a total epiphany. That's fucking so awesome. It's a Calc 3 epiphany. It's endgame Calc 3 epiphany. This equation, this right here is actually the surface area of a sphere. It's just going to change what I teach, the way I'm going to add something the way I teach it in Calc 3. Okay, so we want dr dt. So if we wanted to make a general function for dr dt, we could say dr dt equals, we'll just divide by the 4 pi r squared, right? 1/4 pi r squared dv dt. But dv dt was a constant. It was not changing. It was 3 cubic inches per second. That's dv dt. So dr dt for this soap bubble is 3/4 pi r squared and we're going to end up in units of inches per second after we cancel the inches squared from radius. So that's a general formula. At 3 seconds, or not 3 seconds, when r equals 3, the RDT is 3/4 pi times 3 squared, which is 1/12 pi. Twelve times pi, and then 1 divided by the answer. 0.0265. And that's inches per second. When R equals 6, that's a big soap bubble, right? 6 inches is the length of a dollar bill. We got a soap bubble the size of a dollar bill. dr dt, we're just replacing the r. 3 over 4 pi times 6 squared. This is, let's see, 3 and 36 reduced to 12. This is going to be 1 over 48 pi. (48) times pi. And 1 divided by answer. 0.0066 inches per second. So if air is being pumped into it at a constant rate, when the bubble's small, it's growing faster than when the bubble's bigger. When the bubble's bigger, it takes it more air to make the radius grow as much. So it has to be pumping for longer. Because notice it's faster when it's smaller, 0.0265 versus 0.006. That's 4, yeah. Thanks. All right. So it's quite a bit faster when the radius is smaller. R equals 3 was 0.0265. So only 1 0 after the decimal point, but when the radius is 6, the radius is changing and we get 2 zeros after the decimal point. Because it just takes more air to blow up the balloon just a little bit. And we'll call that a wrap for today. We're going to do more of these on Tuesday. I know related rates can be challenging because they are word problems related, but I think they're actually cooler because I liked them more as a student than the other things because like I could visualize what was going on. Hopefully you'll like it more too.